Welcome to Networks Professionals.
You're always hearing about these incredible futuristic AIs, right? But what if I told you the most important part of AI has nothing to do with some flashy algorithm? Today, we're going to pull back the curtain on the unseen, messy, and honestly, the most critical part of the whole process. Get this, a staggering 80%. That's how much time data scientists spend not building cool new AI models. Nope, 80% of their job is spent on something way less glamorous, just preparing the data. It's the grunt work for sure, but it is the absolute foundation everything else is built on. And it's not just about spending a lot of time on it. Ask any expert in the field, and they'll tell you this data prep is the most critical step in the entire machine learning pipeline, period. So, what does that actually mean? What are they doing for 80% of their time? Well, let's dive into the three biggest problems they're constantly solving. Okay, problem number one, dealing with blank spaces. Imagine you get a huge file of data. You're all excited to feed it to your AI. But it's like a block of Swiss cheese. It's just full of holes, empty cells everywhere. And this isn't just a small annoyance, It's a total showstopper. So what happens when your super smart algorithm hits one of those empty cells? A machine needs clear, precise instructions, right? It can't just guess. It can't just skip over it. It hits that blank space and just stops. It has no idea what to do next. The result? Total chaos. Best case scenario, the whole program just crashes. Boom, done. But the worst case scenario is even scarier. It keeps running, but it spits out results that are wildly, dangerously inaccurate. Think about it. You can't do math on nothing. That null value just breaks everything, sending the whole process either to a dead stop or way, way off the rails. Okay, so how do you fix this? Data scientists basically have a three-part toolkit. First, the simplest option, deletion. You just throw out any row that has a blank space. Easy, but you might be tossing out really valuable info. The next step up is called imputation. This is where you get a little clever and fill in the blank with an average, like the mean or median of that column. And then there's the really advanced move, prediction. You actually use a separate AI model just to predict what that missing piece of data should be. Kind of cool, right? All right, on to problem number two, leveling the playing field. Here's a good way to think about it. Imagine all your different pieces of data are people in a room. Some of them are shouting, and others are just whispering. An AI, left to its own devices, is naturally going to pay attention to the loudest person in the room, even if the whisperer has something way more important to say. Let me give you a concrete example. How do you stop a salary of, say, $200,000 from totally overshadowing an age of 45? To a computer, 200,000 is a huge number. 45 is tiny. So the machine, which only sees the raw numbers, is going to think that salary is thousands of times more important than age, just because the number is bigger. That's it. And here's the problem. That completely biases the model. It becomes obsessed with the salary and pretty much ignores age, even if age is a super important factor for what you're trying to predict. So the solution is to rescale everything. You have to shrink the big numbers and stretch the small ones, so they're all on the same playing field. You force the model to judge them on their actual merit, not just how big the number looks. And there are two main ways to do this. The first is called normalization, which basically just squishes every value into a nice, neat range between 0 and 1. The other is standardization, which is a little different. It reshapes the data so the average of all the numbers is 0. But honestly, both are just different ways to do the same thing, to stop the big numbers from shouting over the small ones. Okay, our last big hurdle. And this one is basically a language barrier. Computers. They are geniuses with numbers. 1 plus 1, calculus, no problem. But when it comes to words, they're totally illiterate. They don't understand concepts. I mean, seriously, how do you explain the color green to a machine that only speaks in ones and zeros? You can't plug the word green into an equation. It just doesn't compute. So how do you translate our world of words into their world of numbers? Simple. You have to build a universal translator. This whole process is called encoding, and it's all about turning things we understand, like colors or cities or different types of products, into a language the algorithm can actually work with. Now, there are a couple of ways to do this. The first, label encoding, seems easy enough. You just assign a number. Red is 1, green is 2, blue is 3. Simple. But there's a massive catch. The computer might look at that and think, oh, 2 is greater than 1, so green must be better or more important than red. Whoops, that's why there's a safer way, called one-hot encoding. It makes a whole new column for each color and just puts a 1 or a 0. It's a way to represent the categories without accidentally telling the computer there's some kind of ranking. And I really gotta stress this point. Getting this wrong is a huge deal. You can accidentally bake a totally false assumption right into your model. The AI then makes decisions based on this mistake you created. This is exactly why one-hot encoding is the go-to for pretty much any category that doesn't have a natural built-in order. Okay, so let's recap. We've filled in the blank spaces, we've leveled the playing field between all our numbers, and we've even taught the computer how to read words. That is a ton of work. So, what's the payoff? Why does all this cleaning matter so much? Well, for one, things get a whole lot faster. When the data is clean and balanced, the algorithm doesn't have to struggle. It finds the best answer way more efficiently. The fancy term for this is faster convergence, but what it really means is you save a boatload of time and expensive computer power. Second, the model actually gets smarter. By scaling everything properly, we stop it from getting distracted by those really big, loud numbers. It can finally focus on the real patterns hidden in the data, not just the stuff that's shouting the loudest. And maybe most importantly, you unlock deeper insights. That whole translation thing we talked about, that lets the machine find mathematical links between things that aren't even numbers to begin with. All of a sudden, it can figure out the precise mathematical relationship between, say, being located in New York City and having higher rent. So when you put it all together, all that tedious, unseen work gives you 3 huge wins. Your model trains faster, it's way less biased, and it can uncover these incredible relationships in your data that you would have totally missed otherwise. This is where the real AI magic actually begins. So in the end, the whole process is a transformation. You start with this messy, chaotic pile of clues, and you turn it into a perfect, clean, model-ready data set. And it's only at this point that you can even start thinking about building the actual algorithm. Which brings us to one final, kind of mind-bending question. If a full 80% of the work is just cleaning the data, it really makes you wonder, where is the real intelligence in artificial intelligence? Is it in the super complex algorithm? Or is it in the careful, thoughtful, human work of preparing the perfect data for that algorithm to learn from?
Thanks for watching.